Okay, so this is a question from current electricity. Here we are given that there is a parallel plate capacitor which is filled with two layers of different materials A and B. So you can see this is a capacitor and there are two layers A and B. So these materials are having a dielectric constant K1 and it is not a perfect dielectric. It also has a conductivity sigma 1. So this material A has a dielectric constant K1 and conductivity sigma 1. Material B has a dielectric constant K2 and a conductivity sigma 2. And this capacitor is connected across a battery of voltage V. So we need to find what is the electric field in the material A and what is the total surface charge density on the interface of these two materials. Okay, so at this interface, what will be the surface charge density? Okay, so let us try to solve this question. Now, you can see that the current flowing through this battery, the total current is suppose I, and the current flowing through material A and the material B, these two currents will be same. Okay, now we know that if the plate area is S, then current density, which is current divided by the area perpendicular to flow of current. So that area is same S. That area is equal to S. So if current is same through both the materials, then the current density will also be same through both the materials. And suppose the electric field, net electric field inside this material A is E1 and in material B is E2. Now, what is the total current flowing through this circuit? Now, for material A, if I want to write the resistance of material A, so resistance, we know that the value of or the expression for resistance is rho L by A. Now, rho, which is the resistivity, can also be written as 1 by conductivity. Okay, so conductivity for material A is given to me, which is sigma 1. Now, the resistance of this material A and resistance of material B, since the current through both A and B are same, so they are connected in series. So, I can say that the resistance of material A, let us say R1, and the resistance of material B, let us say R2, these resistance will be in series. Now, what is the resistance for material A? Instead of rho, resistivity, I am writing 1 by conductivity. Length along the direction of current for material A is D1 and the area perpendicular to the flow of current is the plate area, which is S. So resistance for material A is D1 by sigma 1 into S plus material B. For material B, the resistance will be similarly D2 divided by sigma 2 into S. So this expression gives me the total resistance or the equivalent resistance of the system. So the current that is flowing, I current that is flowing through this system, that current will be simply the battery potential V divided by the equivalent resistance V by R. The current density is same in both the materials. J is same. Now J, what is J? Is the current per unit area perpendicular to flow of current, which is S. So I by S is the current density. Now we know that from the vector form of Ohm's law or the point form of Ohm's law, the electric field E1 can be written as 1 by sigma 1, where sigma 1 is the conductivity multiplied by current density J, right? You must have heard the equation J equal to sigma E. So I'm writing electric field as J by sigma, right? For material 1, it will be, for material A, it will be J by sigma 1. Now, value of J is already known to me, which is I by S, and I is simply voltage V, battery potential V divided by total resistance R. So if you put these values over here, V by R into S into sigma 1. Now the value of R you have already calculated, just replace the value of R over here. You will get the final expression for electric field E1, which is the field in the material A. So this is the first part of the question, which corresponds to option D. Now similarly, we can find the electric field in material B also. If you find the electric field in material B, so E2 will be 1 by sigma 2 into J. So instead of sigma 2 in the numerator for E1 expression, you will get over here V into sigma 1 divided by D1 sigma 2 plus D2 sigma 1. This will be the electric field in material B. Okay, so the second part of the question asks me that what is the surface charge density on this interface? So I am considering sigma is the surface charge density. Now remember, this sigma is not conductivity. This is the surface charge density. Okay. So I've considered a Gaussian surface. This is our Gaussian surface, which is in the form of a small cylinder, you can say, a pill box type of a Gaussian surface, whose flat surface area over here is dA. Okay. So the electric field entering in this Gaussian surface is E1 through this flat face, and leaving this Gaussian surface is E2 through this flat face. And no electric field lines are entering through these curved surfaces. Electric field lines are parallel to this curved surface of the cylinder. So the flux for this Gaussian surface will only be because of E1 and E2, which are entering and exiting through these flat surfaces of the cylinders. Okay, so what will be the total flux? Since E1 is entering, so the flux corresponding to E1 will be negative, which is E1 multiplied by this flat area dA. And the flux which is leaving through this Gaussian surface will be positive, which is E2 multiplied by the flat surface area dA. Total flux will be E2 into dA minus E1 into dA, which is E2 minus E1 dA. And the total flux can be written as the charge enclosed by epsilon naught. So if the surface charge density on this interface is sigma, so what is the charge enclosed over here? On this small portion, you can see that this portion is dA, right? So if this portion is dA, the charge enclosed inside the cylinder will be sigma into dA. So charge enclosed is sigma dA divided by epsilon naught. So from here I can find the value of sigma, which is the surface charge density, is epsilon naught into E2 minus E1. Now you have already calculated the value of E1 and E2. If you put the value of E1, E2 over here in this expression, you get the final result for the surface charge density on this interface, which corresponds to option B.